So our first speaker is John McNeil. He is United Utilities Head of Programme Delivery for the HARP project. John has a rich background in the water UK industry with 25 years experience flexing between engineering, programme delivery and operational disciplines. He has held several senior roles, including delivery responsibility for large infrastructure improvement programmes. John is currently Head of Programme Delivery for the Haweswater Aqueduct Resilience Programme and is enjoying the challenges of leading this once-in-a-generation project. So our second speaker is Nick Sharwin. Nick had a family requirement that's come up very, very suddenly, something he had to deal with at home. He is, as John said, gutted that he can't be here tonight, but I'm delighted that they pulled the strings and he's joining us online, and John will work between himself and you to make it work. So thank you for that, Nick, as well. So he is Head of Construction United Utilities. Nick is a highly experienced civil engineer with over 20 years of experience in designing and constructing infrastructure projects. He has a proven track record in managing complex, multidisciplinary projects from concept to detailed design and supervising construction, particularly on tunnelling projects. Nick is currently Head of Construction for United Utilities and is providing technical support and leadership on the Haweswater Aqueduct Resilience Programme. So, can I ask you, John, to...
Okay, good evening, everybody. Thank you for the warm introduction. Made me blush there as you're going through the bio. So welcome to our evening lecture. This is entitled Securing the Future, the Haweswater Aqueduct Resilience Programme. So again, just to reintroduce myself, John McNeil. I work for United Utilities. I'm the Head of Programme Delivery for the HARP programme. And then Nick, who's online. Hopefully you can hear us, Nick, and you can say hello. No. Okay, he'll join us later, I'm sure. So Nick will be dialed in, but he'll jump onto the sort of his part of the presentation shortly. Oh, is he there?
Yeah. He's behind you.
We just need to unmute him now.
You can see me but can't hear me.
We can hear you now, Nick.
Perfect. Hello.
So that's, after all that, that's Nick's welcome. So listen, it's fantastic to be here tonight. Thank you so much for the invite. Myself and Nick are both chartered civil engineers, so to be in this forum delivering this to you tonight is a real honour, so thank you for having us. This lecture will explore one of United Utilities' most exciting projects we've ever done. As a company, we're super excited about this. We haven't yet started fully with it in terms of on-site, but we've been at this for absolutely years, and I'll take you on that journey tonight. So this presentation is going to focus very much on the kind of early phases of the project. We'll take you through how we've identified the problem, how we've identified the solution, and how we've gone about delivering that so far. So what we're going to cover is a little bit about ourselves, United Utilities. We'll introduce you to the Haweswater Aqueduct itself. What are we doing and why? We'll talk to you about how we're going to do this as well, because this project will follow what for us is a completely novel and new delivery approach, never before done in the water industry, never before done by ourselves. Nick will take you through the technical considerations associated with the project, how we nailed the engineering imperatives really early on. We're going to choose one of our tunnel sections in the Bowland tunnel, which is in the Forest of Bowland, which will just bring to life some of the challenges on one particular tunnel section. We'll talk about planning and stakeholder challenges, and then we'll summarise. So hopefully that will cover and encapsulate the full Haweswater Aqueduct story. The picture behind our mugshots on screen there is Haweswater Reservoir. As we stand here today, it's not that full. We all wish it was, but we, like all the other water companies, are suffering with this lovely, dry, warm weather we've had. So hopefully we can recover from that. Okay, so to kick off, to introduce United Utilities. So we are the water and wastewater service provider for the North West, UK's largest listed water company and the only FTSE 100 company in the North West. And we've got 7 million customers that we are very, very proud to serve. We own a lot of land because we have a lot of reservoirs, as you can see on there, 165. We have a lot of aqueducts to move our water around. We have 88 treatment works, almost 600 wastewater treatment works, and lots of pipe, as you can imagine, water and wastewater pipe. And about 5,500 now skilled employees delivering all that, either in operations, in projects, in engineering, in billing, you name it. But we're here today to talk about only one of our assets. It's probably the most important asset, which is the Haweswater Aqueduct. So the map on the right-hand side of the screen is the map of the Northwest. So you can see down the bottom we've got our big major cities, Liverpool and Manchester. And you can see the sort of blue squiggles in the top, that's the Lake District. And effectively, during the Industrial Revolution, there was clearly massive growth in the Northwest, particularly around Manchester. And we have our water in the north, in the lakes, and we have the people in the south. So Haweswater Reservoir itself was built around 1936 to store water to address that problem. And the Haweswater Aqueduct is what takes the water from Haweswater Reservoir all the way down into Manchester. And that allowed Manchester to grow and develop as we see it today. So it's absolutely the backbone of the United Utilities water system. It's almost like the aorta, if you'd imagine it as a body, that takes the key blood flow to most of our customers. So, key thing to note though, this is a potable water aqueduct. So at the very top of the system, we have the water in reservoirs, we treat it. At the bottom of the system, we have our customers, and in the middle, we've got 110 kilometres of pipes and aqueducts. So this is a food grade conduit, if you want to put it in those terms. So it's 110 kilometres long. It delivers 570 million litres per day. Now, I know that's hard to put into kind of a concept, but it's probably about a third of our complete or an entire sort of drinking water product, if you like, is produced and transmitted by this one asset. So it's critically important to us as a company. Whilst it predominantly feeds Manchester, we also have 18 off-takes as it moves down through Cumbria, Lancashire, into Greater Manchester. So we feed an awful lot of people on the way. So really, really important asset to us. If we were to look at it sideways on, it looks like this. So people ask me, is it an aqueduct? Is it a tunnel? Is it pipes? And it's neither. It's a bit of both, actually. So the Haweswater Aqueduct itself comprises both pipe sections, which we call syphons, and tunnel sections. So the squiggly bits are the syphons, and the sort of white, thicker bits are the tunnels. And so if you can imagine, as you're moving down from the north of the region to the south of the region, you've got rivers flowing out to the sea, the River Ribble, the River Wyre, the River Lune, etc. So the syphons effectively take the water down the side of the valley, under the rivers, and back up into the tunnels. And then the tunnels themselves go flat-ish, little fall on them through the hills, which is what you can see on there. So to bring that to life, here's our imaginary valley. You'd have on the left-hand side a tunnel somewhere buried in there. As the tunnel came to the surface, naturally, the water would then drop into 4 pipes and syphons. It would run down the side of the valley, under the river, back up the other side, and into the next tunnel section. So the Haweswater Aqueduct from top to bottom is a series of pipes, syphons, and tunnels. Syphons, tunnels, syphons, tunnels. That's how it's laid out. So these pictures are fantastic. I love seeing these old pictures. So the HA was built, or the Haweswater Aqueduct was built between 1935 and 1955. So it straddled World War II, where materials were scarce, labour was scarce. But what a job they did to get the water from the top of the system to the bottom of the system without an ounce of energy. This whole thing is under gravity. It was absolutely fantastic. So to give you an idea of how they built it, the picture top left is a picture of the Bowland Forest, or the tunnel under the Bowland Forest, and they used a lot of blasting. So effectively, they'd blast the rock out, they'd bring in the horseshoe steel rock supports that you can see in the picture there to give the initial ground support, keep people safe. They'd then, in the middle, put the steel sliding shutter, which is the picture on the bottom left, and effectively they'd put concrete between the shutter and the outer sort of blast face. So what you were left with was the picture in the middle, the nice sort of smooth tunnel section. Problem with that, in a way, is you don't really know what's behind that inner section, how deep it is, how well it's adhered to the rock. No criticism, a great job was done, but that has come back slightly to haunt us now in a way. Pictures on the top right show how they got a lot of this in and out, temporary railroads, And then not all of the Haweswater Aqueduct tunnel sections are done in that way. Some of it was actually open cut, which you can see bottom right. So, incredibly important asset. It's been around now 70 years, and it's critical to our operation. However, things age, and over the years we've begun to worry about its condition. Now, the siphons that I showed you before, the wiggly lines, they can be inspected relatively easily because there's 4 of them. So you can take one out to inspect it, to maintain it, while the water flows through the other 3, and you can work your way along. However, the tunnel sections are single points of failure. So it's been impossible to go and inspect this without shutting the whole thing off. And bearing in mind how important it is, that's just not been feasible. So, potted history of the HA on those sort of green blocks coming down the screens. As I said, it was built 35 to 55. In the 50s to 60s, there's a little bit of extra work done to it, but really it's bolting things onto it. There was some pipe bridge repairs done in the mid-90s, again, not really integral to the tunnel itself. In the middle of 2000, there was an aqueduct maintenance programme, which sounds great, but again, it really nibbled around at the edges, looking at pipe bridges, discharge pipes. We did try to have a look inside the tunnel by floating some cameras, literally in the live water down, CCTV. Didn't really work that well, as you can imagine, with this thing carrying that amount of water and everything that's going on in the tunnel. So that didn't really pass as an inspection. So we knew when we got to sort of 2010 that we needed to take some other more fundamental steps. And we began to consider the option of just shutting this thing down. We're going to have to shut it down to get in and have a look at it. However, to shut it down and lose a third of your water needs some planning. So we had to invest in tens of water treatment works to make sure that they could run absolutely full chat when we turn this thing off, so that it can provide water to our customers. But the absolute deal breaker was something called the West East Link Main, a project that I worked on, where our system until then was quite divided. We had Lakes water that fed into Manchester, the Manchester system, and we had water from Lake Vyrnwy in Wales that fed into Liverpool, the Liverpool system. And just like the football teams today, Manchester wouldn't speak to Liverpool and Liverpool wouldn't speak to Manchester. So we built a 55-kilometre bi-directional set of pipes between Liverpool and Manchester that effectively joined those two systems. So we can now take water from Wales into Manchester. We take water from the lakes, believe it or not, into Liverpool. That flexibility allowed us the opportunity to effectively take out the Haweswater Aqueduct from north to south. That was an absolute deal breaker. However, it only gave us a window of opportunity. Even with all that infrastructure, that's probably what now, 25 years of kind of planning, it only allows us a limited window to get in and do any sort of work. So, recognising we only had that limited window, our operational colleague said, right, we can use all these assets you've built us, but we can only give you 2 weeks, or maybe 4 at a push, which is not a long time. And that's because whilst we can increase our reservoirs, increase our regional storage, this thing carries so much water, we can't survive without it for too long. So only having that limited time meant we had to plan, and plan, so we could use every minute to maximise that opportunity. So, believe it or not, we created a Haweswater Aqueduct inspection training camp. We trained over 400 people in confined space training, in driver training, in emergency evacuation procedures. So this is people who are going to be asking to go down into these tunnels that have not been in for 55, 60 years. Defibrillator training, self-rescue training, because the emergency services, as we know, will not go very far into the tunnel at all. You had to literally be your brother's keeper. This was that on absolute steroids. Could we get someone out if something happened? So we built this training camp. The big black line across the top is a scaled replica of the HA in every way, dimensionally accurate. We built flat sections of it. We built slanty sections of it to recognise some of the more difficult bits, and we practiced getting people in and getting people out. Water hygiene was absolutely critical, because don't forget, this is a food-grade drinking water tunnel. So what people wore, the disinfection processes, what compounds were in the tyres of the vehicles, what was on people's boots, was the level of detail that went into the thinking around this was incredible to get people in and out, because what we cannot do is leave anything in that tunnel that when we turn the water on contaminates Manchester effectively. The pictures at the bottom, what we call VAS units, so vehicle access system, not the greatest of names, but these were based on luggage wagons that you'd see at airports. And a bit like Trigger's broom, every bit of it pretty much was changed or modified to suit this application. So the seating arrangements were changed to get the right number of people in. The wheels were chamfered so they could drive down a curved tunnel, because don't forget this thing's a circle in sort of a profile. We created little platforms along the sides, which you can see on the middle bottom photo, so when people stepped off, they weren't stepping onto a slippy side of the tunnel. We managed to get a toilet on there, believe it or not. So I can remember many a conversation with our water quality people, and they said, do you really want to take a toilet into a live asset that's a drinking water asset? But we were able to design something there, because don't forget, once the surveyors and the people are in the tunnel, they need to be staying in the tunnel for a full shift. Some of the tunnels, the longest tunnel of the HA is 16 kilometres, so it's 8 kilometres at its longest point in and 8 kilometres back. These things, as they look, don't go the fastest, so it could be an hour or two until you actually get to the middle of the tunnel, and an hour or two back. So it was in everyone's interest to get people in and out safely, but keep them in there and keep them looked after. So again, the level of details that went into things like batteries, food, lighting, ventilation, communication systems, even the butty boxes, believe it or not, were custom designed for HARP. What they put in the butty boxes, there was a limited amount of things you could take in. We didn't want anyone to get upset tummies, so there was no chicken tikka or fancy things like that. It was very demure sandwich fillings. And we had a massive contingency process. So if we lost a crew, somebody got ill, and spread it around the crew, particularly something like diarrhea or something like that, they were off the job, but we needed someone else to replace them. So we had people sat in hotels for that 4-week period just waiting to be drawn into it. This made TV, so again, if you're a geek like me and you remember The Watermen, which was on BBC Two, they did a series all about United Utilities, and at the time we were delivering this outage programme, so they were called the Aquanauts. That's the picture on the bottom right there, and this was the team that went in and did this work. Really interesting anecdotes from the training camp all the time. We had all sorts of roughy-tufty construction operatives rocking up. You put them in that tunnel and you shut the ends off and you have them do some things for a while, and it soon sort of made you realise who was kind of ready for that environment and who wasn't. You know what I mean? It's not for me being stuck in there for a 12-hour shift, but we had to plan and make sure people were ready mentally, physically and safety. So a huge endeavour to get in just to look at this asset. But we did it, and we've done it twice now. So we went in 2013. This was an initial inspection just to look in and understand the condition. So the picture there on the top left is the top of the aqueduct. We put some concrete upstands in, we chopped a hole in the roof, and we dropped the vehicles in, and off they went. That told us a limited amount about the tunnel, but it reinforced the fact we probably need to go back in to do some more in-depth investigation. So we went back in 2016. We shut the whole of the HA tunnel off again, and off we went again. This time we did more detailed investigations, and we made some small patch repairs in areas that worried us the most. So the picture bottom right is a really interesting sort of technique where we took a whole load of collapsed in on itself steel segments, and we designed a system that would deploy these against the side of the aqueduct on the VAS unit. So we've been in twice, and we did see things that concerned us. We were able to build quite a comprehensive picture of what was in there. So you can see the range of surveys we were able to carry out, whether it's GPR surveys, EDM surveys, water quality, 360 laser surveys. You can see the pictures at the top about how the VAS units were adapted to get specialist equipment in. We took some cores, we filled them in before we came out. But after those two visits, we really began to understand what was going on in this aqueduct. And it raised some concerns, two concerns really, and this is what is driving the whole of HARP. So we had a concern about water quality. So could we, hand on heart, say this thing was going to remain a pure food grade product conveying tunnel in the condition it's in? We think we needed to act on that. And secondarily, there was a broader supply to the interruption of water. So if, heaven forbid, we had a structural collapse, then again, having dirty water is one thing, having no water is a completely new ball game, because obviously you can do boil water notices, you can flush your toilet with dirty water. If you don't have any water, then it's a whole different different matter. So really, they're the two risks that this whole programme is trying to address. We did spot a really worrying part of the aqueduct when we came out, and we immediately mobilised to fix this because it was in need of immediate attention. So we've been in already, and one particular section we've kind of bypassed. So if you remember the 4 wiggly lines, the 4 siphons, we broke into those. Again, this is now the 3rd outage. We connected pipes into that. We ran the pipes along a length of the tunnel and connected back into the tunnel, bypassing this sort of concerning time. So we replaced about 2.6 kilometres of the tunnel. It cost us £36 million. In terms of this, to give you an idea of the scale, those pipes there that you see the 4 people stood in front of, they're 4 1.6 metre siphons. Hygiene in the middle there, again, absolutely critical, as it always is on the HA. And one thing that we did in UU, which for us at the time was really quite innovative, is on the bottom right, we were able to use CAD and 4D modelling to do like a 4D rehearsal of how this is all going to play out. And we've never done that before. You know, where machines are going to go, what are the lifting circles, where's plank going to go, where's equipment going to go, where can people walk. And it literally allowed us to make these vital connections far shorter than it would have done had we not had that sort of planning. So fantastic to get that bit out of the way. But that was only a bit. We still had the rest to sort. So once we'd put that bit to bed and we'd addressed that, we sort of sighed a bit of a relief, took a step back and started to reflect on, right, what is it we need to do going forward? What are the requirements to address those 2 risks we mentioned before? So key thing is to address the risks, as I mentioned before. We need to provide best value for customers. We're a regulated monopoly business, but we are regulated by Ofwat, our economic regulator, so it's critical we look at a solution that gives best value to customers. We're keen to be able to monitor water quality and supply characteristics better than the old tunnels ever gave us, whatever the solution was. And we needed to obviously factor into our thinking, how do we make the old tunnels safe? So with those requirements in mind, we set about looking at options, and we really cast the net wide on this. So we started off with over 300 options. We course filtered it down to 50, to 30, to 10. We got into fine filtering, but we looked at everything. We looked at, can we simply go into the existing aqueduct and just patch it up, make a few repairs, it'll do. One option. Can we convert it from being a potable water tunnel to a raw water tunnel? So we have raw water coming all the way into Manchester and build a super treatment works down in Manchester. Another option. Can we treat it en route? Can we line it? Could we close it down altogether, get rid of it and look for different abstraction options elsewhere? Manchester Ship Canal, groundwater supplies, River Dee, etc. No stone was left unturned. We looked at absolutely every option. This whole while we're in communication with Ofwat, sharing our ideas, giving them an idea of the way it's going. We looked at capital cost, operating costs, carbon. We had customer focus groups, willingness to pay, because this is going to be an expensive job, right? So we had acceptability panels. Would you be happy to pay X amount on your bill if we went with this option or this option? And obviously looking at environmental and service benefits. So we did all that, and what we came back to is that at the bottom, the preferred way forward was actually to create new tunnels to replace the old. And you kind of think that took us probably 3 years to get back to the answer where we started. But it was a job well done and gave us that surety that was the answer. And so that was it. So HARP was born at this point, the Haweswater Aqueduct Resilience Programme. So resilience is the key name in that. We're replacing what we've already got to make it more resilient for future generations. So the Hall Bank bit I mentioned already is that little red square on TO2. So we did that little slither, that bit's done, tick. We just need to do the rest. So there's 50 kilometres of the 100 kilometre HA, 110 kilometre HA that needs to be replaced. And we talk a lot in the office about this being a once in a generation project. This thing's been running and serving us well for 70 years, and the team want to build something that's going to last like 120 years, far beyond, you know, my generation, the next and the next and the next. And that kind of sense of grandeur and privilege sort of permeates throughout the team, like it feels special to be involved in HARP. Projects like this don't come along very often in your career, and to be honest, it just feels special, it feels different. So there's a real sense of excitement. Despite the hard work, it feels something great to be involved in. So I'm just going to show you a little video now, just to bring some of that to life.
The aqueducts now of great importance to Manchester district, to the surrounding industrial area, and to many water undertakings supplied in bulk by Manchester. The ultimate and far greater importance of the Haweswater Aqueduct, when 100 million gallons of water a day are being delivered, will surely cause future generations to be very thankful for all that has been accomplished.
Okay, so that first bit has all been about what we plan to do and why. Before we jump onto the technical aspects, I just wanted to explain the how, and it's how we're going to procure this. So, as a UK water company, our economic regulator, Haweswater, are always looking at ways of encouraging more efficient ways of delivering schemes, particularly schemes at this size, for the benefit of customers. And DPC, or direct procurement for customers, is one of those such approaches. And this is applicable to the larger projects. So we're the first to step into this as any water company in any project. There's other projects coming behind us, but we're always told we're a Pathfinder project, which sounds great and exciting, but it can often mean things that can be a little bit clunky, as we're the first one to knock down the kind of fences, if you like. So just to explain what DPC is, as simply as I can. So top left is the kind of traditional approach that we and any water company would normally take to delivering projects. So we're sat in the middle. We provide assets, operation and maintenance services to our customers who pay us for it. We're regulated by Ofwat, who sit above us at the top. We raise our own funding through finance partners. And then if we wanted to deliver any capital improvement or capital projects, we'd engage with a contractor direct or a design house direct, and we'd pay them direct. Nice and simple. That's what we've done for years and continue to do today. DPC changes that a little bit in the sense that it introduces a new party called the CAP, the competitively appointed provider. Our relationship with our customer stays the same, our relationship with the regulator stays the same at the top, but we now have the CAP. And the CAP comes in and effectively raises their own finance to pay for the project. They engage designers, they engage contractors, they operate and they maintain the plant. So it's a little bit like PFI in that sense, in that the CAP, as we call it, will be doing a far greater scope than perhaps we're used to. And we engage the CAP through something called a project agreement. So in a nutshell, that's the kind of DPC approach. But as with everything, there's different flavours of DPC as well. You can have an early model or you can have a late model. What we mean by an early model is down the left, we've got the kind of broad sort of phases of a project with need, optioneering, design, surveys, procurement, build, maintain and operate. So an early model would be the appointee, so a company like United Utilities would identify the need, they might do high-level optioneering, and as soon as they've got any semblance of an answer, they'd put that out to the market, and the CAP, the competitively appointed provider, would take it forward from there. They would develop the design, get the consents and planning in place, build it, maintain it, and operate it. The late model is a slightly different twist, obviously, where the appointee holds on to it for a bit longer. So they might develop the design themselves to a higher level, they might initiate studies, get the planning in place, and procure it a little bit later. We chose the second option for HARP. We went for the late option, and the reason for that is we felt in the interest of our customers, they would benefit by us de-risking the project by holding on to it that bit longer. So bearing in mind the characteristics of the HARP project, tunnelling, ground, having an understanding of the ground and the ground characteristics and the risk, we felt would be better to do that before we approach the market. It also allowed to de-risk the sort of schedule breakers, so purchasing land, getting planning in place, things like that. We thought we can do that. That will obviously make it a less risky proposition. And it also gave us, crucially, the opportunity to warm up both the markets and also the supply chain, because this is new for us, right? But it's new for them too. So that time allowed us to engage, and we did engage with several market engagement events to get people comfortable with this model and this approach. You'll notice the kind of other little bit on the far right in our approach is the operate. Normally under pure DPC, that would be done by the CAP, but recognising again, HARP is a fairly benign asset in that it's gravity. It doesn't need too much operation. So again, rather than paying somebody else to operate the asset, we felt it was again, better value for us to do that. So our CAP on HARP will finance, design, build and maintain the asset and retain ownership of it for the concession period, which is up to 25 years. So that's the model we took. We haven't done this by ourselves. We've got a really good engineering department, capital delivery department, but we need help with this. So we've had a flurry of partners to get us where we are today. So you can see where we're up to with the ticks on the left there. So we're up to procurement. That's the phase we're in now, and we're just coming to the end of that. But many people in the room are in organisations that have supported us along the way. So Jacobs in the initial design, an absolute flurry of geotechnical support throughout that phase, which Nick will touch on. In the planning design, we engaged with Jacobs again and also Costain to look at early contractor involvement, which was possible because of the late model. We're now in procurement, so the legal and financial support services are in place with Addleshaw Goddard and EY. And the exciting news we've been able to let loose over the last few months is we've moved now to preferred bidder on both the CAP, which is a joint venture special purpose vehicle between Strabag and Equitix, and also our ITA, our independent technical advisor, who will sit with us on the project and help effectively monitor progress and certify the end product. And that is a combination of Turner & Townsend and OTB Engineering. So we're delighted to have those parties almost fully appointed, preferred bidder status at the minute, but we're geared up and we're really excited to take them through to the next phase. So that's where we are on the overall timeline. Like I say, it's been a long-running beast, this. We are here just at the end of that tender activity, and we're looking to step into financial close or contract award in the coming couple of months. We then are looking at probably a construction period of about 8 years, 7 to 8 years, and that's looking at multiple tunnels being driven at the same time. So hopefully we'll have a brand new aqueduct come 2033, and then, like I said before, after that follows the 25-year concession period where the CAP still owns and maintains the asset. Okay, that's me. Right, I'm going to hand over to Nick now, who's going to jump into some of the technical considerations of how we've got to where we've got to on HARP. So I'm hoping the tech works. Oh, he's there. Brilliant.
Hopefully, John, you can see me. Can you hear me?
Yeah, we can see and hear you.
Brilliant. Okay. Thank you for bearing with me the fact that I've had to dial into this. Yeah, I'm sorry for not being there in person. So as John suggested earlier, my name's Nick Sharwin. I'm Head of Construction for United Utilities. And today I'm just going to sort of delve into a couple of the aspects around the technical considerations on HARP. So we'll be looking at the engineering imperatives, which building on the work that John's done, those things that the organisation as United Utilities deemed important that we wanted to cover. We'll look at some of the design aspects of how we looked at the design, including the reference design that we developed with the early contractor involvement in Costain. Criteria we determined on TBM selection, just really setting the framework around that. We'll deep dive into the Boland Tunnel, just to draw out some of the technical considerations and the challenges that we overcame, and then the summary will just summarise the where we've got to with that. Okay, so we'll go on to the engineering imperatives. So this is really what, from an engineering point of view, is important for United Utilities, and some of them are actually sort of enshrined in what we call our output requirements. So just the really things that are really important to us. John's already touched on the fact that it's a potable water tunnel, very different from a tunnelling point of view. The fact that this will be carrying potable water, so the work we're doing around water tightness as an example, for the water quality. Really important that we can be comfortable and confident that the asset that we do look to design and construct does provide us that water tightness to ensure water quality. The other thing we're sort of talking reputation-wise, very key, the engagement that we did, John spoke about earlier, to get to where we've got to so far, really engaging with the supplier, with the customers, really engaging with them to make sure that this is going to enhance our reputation. The length of the aqueduct all the way from the Lake District right down to Manchester means we are dealing with a huge different number of communities and stakeholders and customers. So we really needed to focus on that and make sure that we were considering that. John will cover more details on that in the upcoming slides. Connections, we've sort of, it's really interesting just to think about HARP as a tunnelling job. Nice and easy tunnelling job, honest, like all tunnelling jobs, but the connections can be somewhere where it can be a little bit more difficult, and certainly when we do interface with operations, making sure we do that appropriately. John's explained the challenges around getting outages for this aqueduct. So any of the connections that we're looking to do, we needed to make sure that we had a good understanding what we needed to do and what the controls and the engineering imperatives were around that. And then onto the design, a couple of things to call out really. We were looking for a one-pass tunnel. Hydraulic performance is really key. You know, spent a lot of time 70 years ago making sure this asset ran by gravity. Really important that we ensured that this thing continued to run by gravity. The last thing we wanted to be doing is having a massive impact on operational costs and adding extra carbon into the solution through that. Durability, as John suggested, it's lasted 70 years. We're looking for another asset that will last 120 years. So really making sure that we can deliver that from an engineering point of view. And then just talk through a couple of them in the slides that pull forward. I'm going to start with carbon. So just look at the carbon approach that we took on HARP. So large infrastructure projects typically come along with large carbon impacts. You know, I don't think there's unusual for people to see that, but we recognised as the project team and working with our partner Jacobs from a design point of view, we started thinking about this early and looking about how we can actually baseline what we believe the carbon impact would be. So we baselined that early to get an understanding of that, which was good from our point of view, because what it did do, it then started to identify some early opportunities. You could look for your biggest wins, look where the impacts were, and where we could look to try and do something differently. And with it being the late model we went for, there were real opportunities that as the appointee we could get into. So John's already spoken about things like land and getting purchasing in place. One of the big things we've put in place is around power. We're all aware that tunnelling machines are a hungry beast, and getting to some of these sites is difficult. They are in remote locations. So if we hadn't grabbed that early and got the services in place, we would have been running these tunnels on generators. So we really looked to grab that early, make an impact on that. The other one with things, the picture, you can see there, it's an old quarry. We looked to secure the use of that local quarry very close to the Bowland Forest tunnel. So we're going to work with there just to minimise traffic movements, but also minimise and enable that reuse of that tunnel material. So once we did that, we took it to as much as we could do. We then started to look at how we can look to measure performance through the project and ensure that the competitively appointed provider, again, was taken on that journey with carbon. So within the PQQs, the pre-qualifications, the invitations to tender, the tender scoring, there were all measures within there and questions allocated around carbon to ensure that we continued on that with ultimately the contract has some strict sort of targets to outperform the baseline and look to see where we can really maximise that through KPIs. So sort of building a little bit on that and going a little bit off topic, I just wanted to talk a little bit about the Net Zero Tunnelling Group, nothing to do with HARP specifically, but something that I've started to get involved in, and some of you may have already heard of it and some of you hopefully have heard of it and are actively involved in it. But This is a new group that was launched last year, linked with the British Tunnelling Society, subsidiary of the BTS. And the purpose really is just to accelerate the progress towards net zero carbon tunnelling by sharing knowledge and ideas and shaping best practice. So there's a couple of things there. There's a QR code we can share. A couple more slides just to who we are, just some of the people, some of the faces there you may recognise. There are more people actively getting involved. And just to give you an understanding of the first sort of 6 action groups that we've developed, just to try and help drive the tunnelling industry particularly forward with this. So the digital tools about carbon calculations and measurements, really important that, because I think everybody's got a slightly different way of doing that, and to really drive this forward there should be a standardised way of doing it. Looking at design, what impacts can we have from a design point of view? Material use, look to see innovative materials we can look at. Just a step-by-step guidance of how we can look to support carbon reduction within tunnelling, mapping along to PAS 2080, again bringing that along with within the industry, making sure tunnelling aligns with that, and then exciting opportunities around geothermal engineering from underground structures. So there's a few names there, and just to help doing that. So if anybody is interested in joining that group, please contact us. And again, just share the information, allow people within the industry to understand that this group is about. It's a fledgling group, it is starting out, but the more people that look to get involved in it, the more we get a chance to spread the word about it, the more impact it'll have. So a bit of a plug there for the group. So we'll go back into HARP now. So level of design, quite interesting. We had lots of debates about the level of design that we might want to undertake. Very conscious that there were certain things that we were looking at that we did need to sort of firm up from ourselves, make sure we were comfortable with the level of design that we're going to, some of those engineering imperatives and the outcomes that we were looking for. As a business, we needed some element of certainty around that from a design point of view, from a water quality point of view. But there was also areas around planning to get this moving, this project. We needed to get the planning secured, the environmental impact assessments that needed to be undertaken. So some of the ways of working, some of the methods had to have been developed to a level that would enable us to be confident in having these discussions, gaining planning consents, etc. So we look to identify those design outputs and understand how far we would take them as the appointee. So quite small, and there's nothing that you really sort of need to read on the screen. Typically, we're aiming for that developed design point of view 3 on the REBA plan of work scale. So that was where we were sort of looking for. Some of it we only took to level 2, the concept design. So things like the real sort of structural calculations and components around the tunnelling and shafts, absolutely we'll take that only to concept design. Around the buildings and the other surfaces that people will see, the features that we might see on site, we took that through to the developed design, and then the technical design, we took things like the drive strategy, just to make sure we understood what the impacts would be from an environmental point of view and help for the planning. So just a various approach to the levels of design, which worked pretty well for us. I think that was a positive thing that we looked to do. Next one, the reference design. I'll sort of touch a little bit on the reference design. So again, it's building on the DPC model that we look to work with, the late model. So again, we had to support that. There were some elements of the design that we needed to take further to help with planning and the consents. For example, John's spoken about the ground, really important for any tunnelling job and shaft sinking job. You've got to understand the ground. So we needed to make sure that we could get that on. We did utilise the early contract to evolve in Costain with this. So we appointed Costain as our ECI, and they help support to identify some of these key considerations as we work through this design and determine solutions that could be implemented to overcome those key considerations. But we were always minded just to to be aware of the flexibility, we had to leave the cap. We couldn't be defining all these things to the nth degree, specifying, tunnelling machine specifications, writing those type of things. We had to make sure it's proportional to enable that flexibility, to drive that opportunity for the cap to innovate. But there were specifications that we did look to provide, back to water quality, the water tightness, the longevity, all those type of things. We made sure that we specified that, ultimately confirming that we did have a deliverable solution. We wanted to make sure that the design was developing in a direction that could be delivered ultimately by the cap, and somebody would happily pick it up as the competitively appointed partner and go on to deliver it. We wanted an element of cost and programme certainty, so the design had to go to a level to be able to support costing within our own organisation, justify the business case and keep the regulator up to speed with where the costs are going, what the programme will look like, and it will help support the stakeholder engagement. People want to know with some element of certainty where this project is going, what would happen, what wouldn't happen, what does this mean for me, things like simply traffic movements, and things like that they want to know. So we'll sort of move on to a couple of the key factors now that we looked at for the tunnelling. Again, there's many sort of ways that you can determine what these factors might be, but we just set out a framework for all of the tunnels that we looked at, just to really sort of step through the each factors that we thought needed to be confirmed. So again, no real shock here. We're going to start with the ground on a tunnelling job. So just trying to understand what that expected ground conditions would look like, strengths, jointing, pressure, gases, atmospheric things, water flow. Then what is the groundwater condition that we may be coming up against, pressures, volumes, that type of thing, permeability. We have got the tunnel lengths and the drives. We needed to look at those. We have got the anchor points for the wells, for the siphons, as John's shown earlier. There isn't much you can really go away from that point of view. So you have got the ultimate length almost defined from that. Diameter wise, the hydraulic requirement for the diameter is about 2.6 ID, 2.7, something like that. That was a minimum. That was something that we defined early on. It had to pass a particular flow. We didn't specify a diameter. We just specified a flow that we wanted, a volume we wanted through the tunnel. We wanted it to convey it by gravity. Vertical and horizontal alignment. Again, there was flexibility on that, but it had to flow by gravity, and we had to tie in with the siphons. So there was an element of flexibility rather than true flexibility. We wanted to make sure we had a good understanding about the locations that we were looking to work here and the spaces required. Most of this was focused around the wells, around the connections that we had to make, trying to manage the tunnel lengths so we were close enough to the siphons to make the connections, but not too close that we had an impact on those existing structures. And this ultimately led into the procurement strategy and availability of the machines. We've got 6 tunnel sections. There was lots of debates around balancing getting 6 tunnel machines and having them running concurrently, having one machine to do it all. There were those sort of discussions, and in between what would be the appropriate thing, and then having a think around alongside that about production rates. What is particular machines and likely production rates going to be, and how will those programme constraints impact on the other tunnels and potential connections back into the system for the outage. Those were some of the key factors we considered. So building on the first one for the ground, I think when we first started to have a look at this, and you look through lots of the old historical records, you've seen some of the photos that John put up there in the video. Got some really, really good photos for and geological records, geotechnical records for the existing Haweswater Aqueduct, lots of face records, lots of drawings, everything from that point of view. So that was a really good starting point. But obviously we're not going to build the tunnel exactly where the existing tunnel was. So the face records, although they were interesting, they weren't necessarily a true reflection of the route that we were going to pick. and give us an understanding of that. There was definitely a challenge around the ground investigation up in the north, very remote access, and central sections area of outstanding natural beauty. There weren't lots of historical records around there in terms of others using the BTS records. And as you got towards Manchester, there were lots of good records, but again, access constraints, industrial areas trying to get access to these wasn't particularly difficult. So we worked really hard at thinking about how can we get enough information about the ground to provide us with confidence, but also supply chain with confidence that we have got an understanding of this ground and it can be managed and it can be priced appropriately and we can understand it. So we worked really hard to look at geophysics. We looked at shallow geophysics, deep geophysics, and we did some boreholes. But again, considering the 50 kilometres of tunnelling, we've got 149 boreholes. I think that's, I wouldn't say it's light, but I think it's on the lighter side, I think. But we supplemented that with the geophysics, groundwater monitoring, and we worked with the BTS and from a water industry point of view, first to build a 3D geographical model. So with the boreholes that we had, the geophysics that we had, some targeted areas for around some faulting zones and things like that, we were able to build a really good 3D model that helped us ultimately develop a robust geotechnical baseline report and a GBR that the market were comfortable to work with. So we'll go on a little bit more about Bowland Forest. We've sort of picked that really. I think if you look at that section that John put up, the one on the screen now, it's the interesting one for me. If you're looking from a tunnelling point of view, it's the longest tunnel drive there. It's the deepest tunnel drive. So your eye, or my eye, is ultimately drawn to that. Initially, it was right. What's going on in there? That looks interesting. So we'll run through some of those sort of key challenges that we've got there. So a little bit about the Bowland section, Trough of Bowland. Anybody that sort of do it, you've got the Forest of Bowland there. So the graphic on the right hand side just sort of show we are in the middle of nowhere. You can just about make out that it's a bit of a forest and we are going over a fell. The photo on the left is just an indication of the remoteness of it really. There's sort of one long track that meanders across the fell and not particularly easy access. That's what we had. So it was remote location, really sort of rural communities as well. The last thing they were probably expecting when we first turned up to say we were going to start building a new tunnel through there. I think some of them were unaware that there was a tunnel there, if I'm being honest. Lots of farming, environmental impact, area of outstanding natural beauty. We had the Osprey in the area, triple SI, lots of things that you would expect looking at a Google map of the area. Nice part of the world, and lots of people for tourism and that type of thing. Doesn't make it easy for building tunnelling projects. So if we look at the technical aspects of that from the next and what we considered, again, trying to show there with the graphics on the right hand side, the depth, 300 meters plus tunnelling, not something that I've been doing or you typically expect to do within the UK, I don't think. The bottom section, you can see the blue line is the existing HA. The others were options. Really, we looked at a number of options on all of the drives, but particularly in the Trough of Bowland. 16 kilometres, we were very, very sort of nervous about that length of that drive. Is that something that we can do at this diameter? Are we sure we can do that? We did look at alternative locations for intermediate shafts. The green area on the bottom right-hand graphic, it is the area of outstanding natural beauty in the triple SI. So looking to build anything within there became very difficult. You saw the sort of access to that. And ultimately, you'd then have to put an intermediate shaft that was circa 300 metres deep. Again, not a particularly easy task to be sinking a shaft that depth. And what benefit would you get from that? ultimately if you were doing that. So access was very difficult from the northern section, so the one on the left hand side of the graphic. So we had to drive from the south. That became quite obvious quite quickly. Just getting vehicles to the northern section, HGV vehicles was difficult. So that became the obvious drive location, driving uphill from that point of view. The ground and the geo-environment, the ground is rock, predominantly rock. We've got siltstones, sandstones, mudstones, that sort of conglomerate of things. There are a number of fissures there that we found. There are some faults that we investigated with the ground investigation just to confirm. And the groundwater became very interesting when we did the HA section through here initially with the inspection. We did do some rudimentary sort of crude monitoring of the pressures that were coming into the tunnel, which inferred at that point in time that there were maybe 17 bar pressure, so significant pressure there really. So we needed to do some ground investigation and understand, is that pressure true? Is it real? And ultimately it sort of turned out to be even more there when we did do some of that. But we had to look at that from a shaft construction point of view as well, where we could put those compounds. And based on all that, we went through the TBM selection that I spoke about before, which we'll cover. So I'll look at a couple of the areas of these technical considerations now, just to try and bring it to life. So again, access, we've spoken about the challenges and the difficulties getting across the moor there. So site locations are typically significantly distances from major infrastructures. We're looking at rural roads here and through rural villages. We worked really hard with the Costain to understand what traffic movements would look like, working hard with the council and locals to just figure out how we can make this project work. We're not going to be nipping in and nipping out here. We're going to have to be here for a number of years, so we need to make sure that we minimise that impact on the customers and the local community and the environment and the businesses. So the graphic on the right hand side just gives you an idea of the diversion routes that we're likely to have to put in place and how that can have impacts on the community. The bottom right hand graphic shows to get to the launch compound for the Trough of Bowland. The Bowland Forest needed a couple of kilometre road, ultimately with a bridge across the River Hodder. So again, the bridge was about, that we're putting in, is going to be about 100 metres just to keep you outside of the EA flood zone. So again, significant temporary works and infrastructure that has to be in place before we even look to do some tunnelling. But again, the communication that we've had with the stakeholders and customers, they've been accepting of that and they've understood the approach we've taken. So if we go back onto the groundwater, I sort of touched on this a little bit before. As part of the existing HA inspection, we believed that the water was maybe 17 or 18 bar pressure. Again, there was a little bit of scepticism about how true and real that was. But then we undertook some ground investigation and we undertook some hydrogeological assessments, and a number of times it was coming back to suggest it was at 27 bar. So again, a machine at this sort of utility size, down the 3, 4, 5 metre diameter, operating that pressure is not something that I've necessarily heard of, not something that I've done, and I just don't think it's achievable getting seals to operate like that. We had a good conversation with a number of manufacturers and we found it difficult to look at that from a temporary point of view, but from a permanent point of view, we've already established through the slides, water quality is absolutely imperative for United Utilities. We need to make sure that we have a lining design that can meet BTS class 3 and we can protect that water quality. So how are we going to be able to do that when we've got a potential external groundwater pressure of 27 bar? So we engaged MOTS to look at some lining design. And just to determine, what are the feasibility. We spoke to gasket manufacturers to look to their thoughts, what did their research tell us? What examples did they potentially have to do that? Keeping in mind we were predominantly looking for a one-pass tunnel lining system. So again, real challenge to keep the water tightness class 3. We're conveying potable water. How do we get this to work? So I think in theory we could probably get a one-pass system to work from a design point of view. But I think we looked at it in the round and suggested, you know, just for completeness and to be safe from the permanent works point of view, we've identified that the central 8 kilometres of section will line that, secondary line that, just to ensure and really give us that security around water quality. So that lining became a mandatory requirement, and that went into the scope to suggest that this 8 kilometre section needed to be lined. That was a requirement, along with a number of strict quality assurance requirements, quality control requirements throughout the design, the manufacture, the installation and construction of that tunnel with agreed tolerances. So I've touched on the temporary works a little bit there. Alongside the water pressures in this particular tunnel section, we've got the length of the tunnel, 16 kilometres, again, outside of the norms for this typical diameter utility tunnelling. Not something that we've done in United Utilities. Some people have sort of done above 10 kilometres. I know LPT2 just completed their tunnel down in London at over 10 kilometres. But again, it's not an everyday run-of-the-mill activity to build tunnels at this diameter for that length. So we looked at talking to people, tunnel manufacturers, talking to contractors, and making sure through Costain, we could satisfy ourselves that we could do it safely ultimately. Can we build a tunnel, or can we expect the competitively appointed partner to build a tunnel that's 16 kilometres long at this utility diameter safely? So we had several meetings with the HSE to look at the practicalities of the long tunnel. Really important that we could come to an agreement that a particular tunnel diameter is appropriate for this tunnel length. We looked at the ventilation, the fact that the machine is going to be an open face machine, the ventilation and the atmospheric monitoring, really important to make sure that that was in play. Emergency planning, making sure that we could get a casualty if we required out of the machine, making sure we could do that in a safe and practical way. So we had some recommendations that were put in to confirm that we would have gas alarms, we'd have refuse chambers on the California crossing. We'd make sure we had a dedicated ambulance man riding car positioned on the crossing at the back of the machine. So if we did have an emergency, we have a casualty, we could get them out. All underground personnel would be trained to a very high emergency first aid standard, making sure that that was in place. And all these things we felt culminated in the belief that a 16 kilometre tunnel would be achievable to be able to be delivered. We then did look at productivity. Again, when you're starting to get to these lengths, logistics becomes a problem, or managing of those logistics, the impacts that can have. We just wanted to make sure that we could make it work from a productivity point of view as well, and a programme point of view. So if we sort of tile that back together for TO3, the technical issues, for this particular tunnel, we've got the moderately hard rock for the tunnelling machine. There'll likely be high attrition rates on the TBM. We've got faulted zones that we identified through the geophysics. We did some targeted ground investigation there to prove that those faulted zones were there. There's an option to pre-grout some of those areas to try and tighten that up, because the expectation is that we'll more than likely get the flow of that water and that pressure from those faulted zones and the potential fissures that we might have on the way. We did feel the open face TBM was appropriate. That's what we worked with our reference design. This isn't conformed into the document. This isn't anything that we specified. This was just to allow us to convince ourselves and satisfy ourselves that it was achievable. The challenging access that we spoke about on the terrain meant that the intermediate shafts were a no-go, and could we make it work for the length? We believed we could. So one of the things we did look at with the manufacturers was type of tunnelling machine, and settled probably on a double shield. Again, this is only our opinion, the work that we've done with the manufacturers and with Costain, but a double shield TBM open face would increase productivity and help with the programme constraints, meeting the programme. And then just that allowed us to understand the impacts that it had on the wider HARP project. With this being the longest tunnel, it naturally wants to fall along the critical path. So just to sort of summarise the technical considerations, the real sort of whistle-stop tour there on one of the tunnel sections. There's 6 of them, and they've all got their own exciting challenges that we've had to step through. So I think because we had the late model, we had the opportunity to step through these challenges. I think it was a really good thing that we did grasp the nettle and work with some of these challenges, really drive and understand what that risk looked like and how we could manage that. You know, things like the groundwater, confirming that, I think was a real positive step just to understand what we may have. The proportional design approach that I spoke about before, I think we've delved into areas where we needed to delve into, and we've pulled ourselves back where we haven't had to delve into them. So that's helped us really with that and drive a deliverable solution that is positive. And I think because we understood where our risk appetite sat as United Utilities, we could really help with that proportional design approach where we needed to confirm that, whether that be about water quality or from a customer and stakeholder point of view. We could go a little bit further with the design, but leave opportunity for the supply chain. And all the good work that we did around the technical considerations really did help feed into the stakeholder conversation and support the approach as to why it was and make that a richer conversation. So based on that, I'll leave it there and thank you, and I'll hand back to John, and he'll talk a little bit further about some of the planning and stakeholder considerations on the job.
Thanks, Nate, that's great. So last little bit now, just to sort of round off the lecture. So as Nick mentioned before, doing all that outline design work really helped us to engage with purpose with planning and stakeholder. So there's clearly a vast range of people impacted by this scheme. So HARP being a linear asset, you know, it's long. We've been sort of speaking to 7 different planning authorities. We've needed 9 different planning permissions. So someone told me there was like 1,600 documents that we've had to produce to get this thing over the line, including one with Yorkshire Dales National Park, which from a North West water company was a bit odd, but that was okay. And I'm happy to say they're all now in place. So it's kind of like tick, 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 tick times 9, which is great. We've put in place 2 extraordinary highways damages agreement, because if you think of the amount of traffic this is going to produce, you know, in fairly rural environments. And we're going to be working in areas of outstanding natural beauty, rural environments, urban environments. We're going under the M6, we're going under the West Coast Main Line, we're in remote locations. Huge range of challenges and a huge range of views and opinions from people. MPs and council leaders, because this project's been going so long, have come and gone. So we've had to speak to them and speak to them again. I was up at Lancashire County Council yesterday, being introduced to the new council leader, reform candidate. So there's a whole new set of MPs and council leaders there, right in the middle of the patch. We went big on HARP, like we do on all our major schemes, on public consultation. So we were out there speaking to people, town hall sessions. COVID then hit, so a little bit of an innovation for us on HARP is we took our public campaign online. We did virtual consultations. This is how the virtual consultation room looked. So it's meant to replicate what you see when you step into the town hall. You can click on each thing and understand about the plans, the maps, traffic routes, visual impacts. Never done this before, and we got so many hits, like over 100,000 hits. And loads more engagement than you'd normally get, which is quite interesting. So something we're going to look into going forward. It was the biggest consultation we've ever done. It probably needed to be. What came out loud and clear was people's worries about traffic and how it's going to impact me. So Nick's already talked about what we're looking to do in terms of temporary river crossings, temporary haul roads. We've got park and rides planned. We've got holding areas to avoid any HGVs interacting at any time with school pick-up and drop-offs at certain points. There's a massive programme of highways improvements before we even start doing anything on shafts or tunnelling. But it really shows the importance of engaging early and getting an understanding what the pressure points are with folk. Quick one on land. So we as a water company are pretty well placed on land to gain access to private land to do work. Normally, we would secure the purchase of land for anything we build at the surface, and anything subsurface would cover through notices. But with HARP being on site for so long, we went for a slightly different approach where we've majored quite heavy on land purchase. So buy the land, then it just takes it off the kind of risk, if you like. So some of the reasons we're going to need land are for obviously the drive sites, the reception sites, river crossings, haul roads, transportation hubs, highways alterations. And to give you a view, that's one particular site. I think that is on TR2 that Nick was just taking you through. But the green bit is where we've purchased land. The blue bit's where we're going to lease land. And the yellow is like statutory notice. But we've had to deal with about 88 parcels of land, 200 landowners. But again, we started it with plenty of time to get us to the position we're in today. And the last little bit, so one of our values at UU is to make the Northwest stronger, greener and healthier. And we've really taken that on board with this scheme. So social value and community investment's been massive. I don't know if you have mad science down here, but it's quite a big thing up in the Northwest. My kids go to it. It's a group of scientists, I guess, who are in the local universities, and they come into after school club and they do little experiments with the kids and all the rest of it. So we've hooked up with Mad Science, and they are going to do sessions with every school that's impacted by the project on the water cycle and the Haweswater Aqueduct. And then when we start building, they're going to do a session on the construction practices that go into tunnelling. We sponsored river-related activities, because obviously water companies in the press a lot at the minute for rivers and pollution CSOs. So we sponsored the duck race, which is the one with the yellow blobs in, they're ducks. Trout in the classroom, where effectively we take little trout fry into the classroom, let the kids learn about the fish, they feed them, they get them, and then they release them into the river at the end. And then Huncote United on the far right there, one of our reception sites is actually going to come up in quite an urban environment, and the only place we could really find was where the local football team play. Didn't go down well. We've got ahead of it, built them a new pitch, well in advance of us rocking up on site. They're very pleased with it, or well, we're building it at the minute, but they're very pleased with what we're going to give them. It's an opportunity again to put a bit of investment in with changing rooms and things like that, and really get ahead of the game and be that sort of good neighbour. So that's really it. So in summary, we've covered a lot there. Conscious, I've said here, we've covered a lot in the last 45 minutes. It's been a bit longer than that, so apologies. But the key sort of points, the Haweswater Aqueduct is a big deal for us. It's our biggest, most key asset. It needs resilience, it needs replacing effectively. We're using DPC, Pathfinder, procurement approach. We've really got into the engineering imperatives very early to try and de-risk the project. We've adopted that late model to understand and hopefully de-risk the technical risks. We're currently in procurement, and we're just about to step off that cliff into the next exciting phase. And maybe in the future, if you're interested, maybe we can come back and tell you about how it's getting on once we actually get this thing up and running. But it's been a real labour of love to get us where we are today, and we're looking forward to the next bit. So that's it.
Thank you very much for that fascinating project, generational, as you said. At the back there, could you knock the spotlights down a little bit, please? And then, yeah, that's much better, thanks. So, questions, please. Wow. Yeah, question there.
Hi, Tom Robinson, Strabag UK. Very interesting talk, thank you, that was fascinating. Quick question about the planning process. So there's a conscious decision to go with separate planning applications for all of the statutory authorities on the route. Was an alternative something similar to hybrid bill, Crossrail Act type concept, was that ever proposed or considered?
It's a good question. Wasn't actually involved in the project back in those early days, but we just went down the conventional town and country planning route. I'm not sure whether we ever looked into DCO or anything. Are you aware, Nick?
I think we did, if I'm honest. I won't be able to say more than we did look at it, and the pros and cons were looked at. I think we've got very good relationships with our local town and country planning route, and I don't know whether that played a part, but it was considered, and the experts that we spoke to within United Utilities and externally recommended the approach we took. But yeah, it was, I don't know if there was timescales to get something like that in place or not, but it was considered, but we can take it away and get a proper answer.
Yeah.
Okay. Yeah, question. Yeah.
Hi, thank you so much. Tomasz Szogola, Szobak
sorry.
UK. First question, from your experience to date with the local residents, how they were satisfied or a bit dissatisfied with the current engagement? We know that in the UK, infrastructure projects brings a lot of attention, also protests like HS2. What's the feeling you are getting from the local residents? And the second question, what are your first thoughts about the MAC disposal? Where?
I can't hear.
Shall I repeat? What are your first thoughts about the current experience with the working with local residents following the surveys? Is there satisfaction and they are in support of the works, or is quite opposite?
Yeah, do you want me to start with that one? So before we even got onto putting planning in for the project, we'd also previously consulted with a lot of customer groups to get down to this being the proposed solution. So there's already a feeling of semi-buy-in the sense that I had some input into guiding it. But what probably the real test was the public exhibition and the public consultation. And, you know, we're never expecting people to be cock-a-hoop about this because obviously it's going to be massively disruptive in some areas. But we were really pleased to get knocking on 70% support. I think the slide said sort of 67, 68% of people that were, you know, supportive and understanding of what we were needing to do. Would have been great to be higher, and there's still people we need to sort of bring round. But that gave us a bit of comfort that, you know, we're not going into an entirely, you know, hostile environment when it comes to the customers. But we've made it, I mean, we do a lot of this ourselves, but we've also made it prevail into the construction phase that we have a lot of focus on customer satisfaction surveys. We have this thing called CMEX in the water industry, which is a regulatory measure of customer satisfaction, and it covers billing and it covers when you move house, but it also covers construction projects. So we've made it really important to our supply chain, should we say, and incentivise them heavily to not go in and run roughshod over communities and upset people.
Okay, question here.
Andrew Smith, I'm retired. Thank you for a very interesting and informative presentation. I just wanted to ask about the siphons. As I understand it, they're open cut and river crossings, quite an environmental impact. Did you ever consider putting vertical shafts down and doing the siphons with a horizontal tunnel between them?
So we're not actually going to replace any of the siphons. They're going to remain as they are. And that's because we've got a rolling programme of siphon repair or replacement, because the beauty of the siphons is you can isolate one and work on it over a period of time whilst the aqueduct will pretty much run at full flow. So they'll just be left in situ. Where the siphons connect into the tunnels is the point of interest for HARP, because when we lay or we drill the new tunnels, the question then is how do you connect the new tunnel to the existing system? And you can either go tunnel to tunnel, but that would mean you have to take the whole thing out when you do it, which is very difficult, or you can build a new tunnel, yes, and a new valve house and new siphons. And if we do that, it means we can connect one siphon in at a time, if that makes sense. And we put it out again to the market, set out the two options, and all of the bidders, thankfully, from our point of view, because operationally it's favourable, went for the siphon-to-siphon connection. So it'll cost a bit more in the short term to obviously extend the tunnel, have the valve houses as well, but it just makes it so much easier to commission at the end of the job. So that's the kind of thinking on the siphons.
Thank you.
Hi, Steve Parker, Keystone Tunnelling. Excellent speech, thank you. Just on the water losses, and you were talking about the pressures and everything, it's academic, but was there more water going into the tunnel when you got to Manchester, or was there more losses? Because of the water pressures you're talking about. Was it going out, or was it coming in from the old tunnels?
Yeah, I can't relay completely our findings. Obviously, there's certain things under certain privilege, but there's quite a lot being lost, which is not good, leakage and everything else, but on a drinking water asset, you probably want it that way around. So it'll be interesting to see how much more water we have in our system when we've got a tunnel that doesn't leak, which would be great for our leakage figures.
Rod Young, Bar Hale Limited. What are you doing with the existing tunnels? Are you going to reline them, reconnect them, keep them connected?
No, so what we're going to do is recognising we can't just leave them and abandon them, because obviously it's a huge underground void that could collapse, is where there's infrastructure above or sensitive areas, we're going to reinforce that locally, but then effectively we're going to change them, turn them into almost like a land drain. So they'll be permitted to fill with water, but have a controlled overflow at one end, which will then discharge to, it will actually connect into the new tunnel's overflow and discharge to local watercourse. So the water level will find, the water pressure will find its own level effectively in it, and there'll almost be a benign asset that we'll have there.
Hi, Lena Elbader, Cementation Skanska. I just had one question about, at the very beginning of the presentation, you mentioned that you started with 300 plus different possibilities, and later on you narrowed it down to the new construction. And I guess my question was, what were some of the other ideas that made it to those final stages? What were the metrics that you judged it on? And why did the new build distinguish itself from some of the other ideas?
Yeah, no, it's a really good question. The ones I mentioned before, I was trying to give a picture of the breadth of what we're looking at. The one that probably ran it closest was converting it to a raw water asset, because it being a possible water asset comes with a whole lot of challenges, like Nick was mentioned before about water ingress, water tightness, and kind of they don't go away if you've got a raw water asset, but you're a little bit more relaxed about that. The problem with that then is having to treat it at the bottom end. We already have a treatment works at the bottom end, but it's not capable of doing what we need to do. So keeping the asset but converting it to a raw water asset is quite cheap. Building a quite energy intensive, chemical intensive process at the bottom end kind of tipped it the wrong way. But it's a circle that we've been around quite a few times, because on the face of it, heavy civil engineering to this level, you kind of think, really, is there no greener, more economic way of delivering it? But because the water flows by gravity and will continue to do so, plotting that on an NPV of OPEX against CAPEX, it comes up quite favourable. So that's probably the option that ran it closest.
Yeah, question down here.
Ponampalam Lancashire, thank you. Good presentation. My question is maybe very political, but from my perspective, I know we've spent, or we're intending to spend for 8 years, this construction phase. Currently, as it stands, and which all bankers would like to know, what is your current estimate for this project from beginning till end and after the concession? And the second question to follow it, being a utility company, you're trying to look at your return on investment. So do you have a net present value compared to a whole life costing?
Okay, so on the first question was about the estimate of cost, was it? Yeah, so we've gone to press when we announced the preferred bidder. So the capital cost is looking between 2.6 and 2.9 billion. So it's a massive amount of money. What we're super aware of as a water company is when you layer that, so probably 2 AMPs ago, that was the single biggest investment that you will ever make and have ever made. However, time's moved on, and now in the context of our AMP8 investment programme, which is up to like 11 billion, we've been overtaken, should we say. So what we're super conscious on the MPV is making sure that the bill impact, and that's the way we speak when we talk about HARP, what is the pound and pence impact on a bill? How does that now marry up with the bill impact of the rest of the capital programme? So there is an MPV for all that. It's probably straying a little bit out of my comfort zone and expertise zone, but that factors in capital cost, the operational cost, cost of borrowing that we have to obviously repay, because it's almost like a mortgage model, isn't it? We get it all on the tick, if you like, early doors, but then we have to drip feed it over the 25 years. So 2.5 to 3 is where we're going to start at, and then MPV. I'm sorry, I don't have the I don't have the full facts to relay on that.
All right. Question online. This is from Martin Russell. Did you consider a larger tunnel diameter to really future-proof the structure?
We did. So Nick mentioned before, strictly speaking, hydraulically, it's 2.6. We based our kind of initial design on something bigger than that. I think 3.6 to 3.9, depending on which tunnel section, because it's obviously not just hydraulics, it's feasibility of build and logistics, planning, spoil, all the rest of it. So that would have given us a healthy amount of headroom. And again, without getting into too much detail, what we saw from the market was tunnels that are slightly bigger again, for the reasons of logistics, standardisation, speed and productivity. So I think we're going to end up with a tunnel that's will result in far more hydraulic capacity we need, which is potentially good if ever we were to look into longer term, keel the waters, perhaps would be mentioned in the past as potentially a water grid type connection. I think we're a long way off that, but if ever we needed to, we've got a tunnel that could take extra water. So,
okay. Any more questions? Oh.
Yeah, my name's Barry Willis from IPS. I can understand your choice of machine, open face, with regard to main bearing sealing, but what mitigation are you going to have in place for when you meet unexpected water, especially at the pressures that you're looking at? I've seen double shields flooded in the past.
I'll jump in there. It's a great question and one that we have been toying with, because it is that balance. If we put in a full face machine, I just don't think we're going to be able to withstand those pressures. So we'll go with the open face. And as you say, you need to make sure we've got contingency measures in place to manage and deal with that. I believe we've got a good understanding of where those likely pressures will be. In the mass of that rock, I don't think we'll see those. You've got pressure and flow, haven't you? I think the pressure will still be there in that mass, but you won't necessarily get the flow. The challenge will be when you get the flow through those fissures or through those fault zones. So we've got a good understanding of where those be. There's an approach around probe drilling. So where we do think we're going to be entering those, we'll be probing ahead, looking to do some compensation grouting or do some grouting to tighten that up. The machines will be designed with what we need. From that point of view, we are driving uphill, although it is very shallow. This isn't a typical utility tunnel. It is very shallow, but we are driving uphill. There'll be flood doors on the machine that will stem the flow. They obviously won't stop the flow. The equipment that we have will be rated appropriately to be flooded, and we'll have evacuation procedures in place. We're looking at those type of things. Again, it'll be for the CAP to develop further, and it's ultimately the machine that they pick and they choose to implement. But we'll be asking the questions that you're asking there just again to satisfy ourselves. But we felt with those contingencies in place that the open face machine would be suitably sufficient to be able to deal with those. Is that okay? I know it's a challenging question and one we'll be asking ourselves throughout the project.
Okay, maybe take one more question. Yeah, down the front there.
Hello, Paul Dryden from Transport for London. Having seen the difficulty in understanding the condition of the existing system, can you tell us anything about how the asset condition is going to be monitored in the future?
Yes, so we are keen to do that, but what we're not entirely settled on is how we'll do that. So we're keen to have as much tech, in inverted commas, as we can in this tunnel to stop us having to go in and do the routine inspections. We're just really conscious we're 8 years away from having this thing built, and whilst there's things out there, we're not entirely convinced it's what we might need, or if something better might come up in the delivery of the project. So a bit of a loose answer, but we've broadly specified that we'd like that, but we haven't really figured out how we're going to get it. But yeah, anything we can do that gives us knowledge of that asset, that stops us having to go in, because it's probably the single most risky thing that we've ever done and have done as a water company, is to turn this off, and we don't want to be doing it very often. So yeah, the ambition's there. I just don't know what it is. If it's fibres in the segments, doesn't sound particularly elegant. Is there another way of doing it? Can we use drones and have smaller outages? I don't know. There's a few things knocking around, but yeah, as much as it can speak to us and tell us its own condition, the better, really. But we'll see.
Thanks. There's a final one online here from Mariana Edward. What strategies are in place to manage groundwater during tunnelling?
So very similar to the question that we had. For the lower tunnels where we have 5 and 6, there's potential for coal mining at lower groundwater pressures. So we'll be using a closed space machine now. We'll be using slurry machines, so that was the recommendation that we came to as part of the reference design. So a lot easier to manage those flows. Those machines will be designed and capable of withstanding those pressures. Where we do have open face machines in the northern section, potentially, as we've spoken about in T003. Again, it's the contingency planning there about identifying where we think the water flows will come from. Can we do that probe drilling that we will have potentially over the weekend, get those probe drilling 100, 120 metres distance, grouting that up as we come along, and then managing the advancement and controlling that flow of water, large pumps on the machine, driving uphill, flood doors to sort of stem the flow rather than stop the flow, equipment that's appropriately rated to be flooded, so if we do get a big flood, we can manage that. I think what the historical documents did show us when we did look at the face of the machine, the face of records that we had from the original ones, a lot of these waters that they did come into contact with, they did subside. So there was a big peak of water flow that came in. Once that pressure was released, the flow then dropped off to be manageable. So again, the approach would be just to be able to deal with that initial flow and then manage the lower flows with pumps and things like that. It is a challenge. Any groundwater on a machine is challenging.
Okay, can we have a final round of appreciation, please? Right, just a couple of slides to run through and then we're finished. So, food and drink tonight. Food sponsored by Burrows Conveyor Systems, thank you very much. And the drinks sponsored by Normet. You don't have to clap every slide, but the BTS YM lecture in June, 5th of June, the Los Angeles Outfall Project case study, and that's been sponsored by Senna. What we got next? Then the Thursday, the 26th of June, this is a nice thing. So the BTS Bridging the Gap between the industry and academia. We're trying to do a lot of this now, encourage the youth and coming into the industry. And there is a collaboration session there, all day in person at Nottingham University. Anyone interested in tunnelling can attend. So that's Thursday, the 26th of June. Oh, it's not on my thing. All right. Thursday, the 19th of June, design of tunnels for the Prague Metro D line. Yep, that's the BTS evening lecture. Last one before summer. We've done that one. So the annual dinner, closing the bookings tomorrow, Divik, is that right?
Yes, but if anyone's still interested, they can drop me a line. But the bookings will be formally closed tomorrow after weekday.
Yeah, so pretty full house there. Next Friday, week tomorrow. BTS Design and Construction course, so that's a 5-day one, 30th of June to the 4th of July. Always very popular. You need to get in quick because we can only guarantee the next 10 places. So a lot of the places are filled up. I'd encourage you to put people on it as well. It's a very good course. Many top people from the industry giving lectures. Yeah, the BTS YM conference, 24th of October. That's very keen to get people to sponsor that, companies to sponsor that. We have some sponsors, but keen to get more. All right, so the BTS at 50 book. We had great feedback on that, I'm sure, as you all know. They are still available, some of them anyway, at £65. And we're also going around linking up with universities, donating the books to the libraries, again, to foster links into tunnelling for people early on in their careers. So it's been a real conduit for that, and we want to continue that. And that's it. So, evening's over. Thank you very much, everyone. Sorry, I forgot one thing. Feedback. So while we're booking in online, it's your opportunity to give feedback on the lectures and anything else. And there's a QR code there. Thanks. It was almost faultless.